This is the third recording of Chapter 2 presentation with slides. In the previous recording, we stopped at limits involving infinity and asymptotes of graphs. Let us see what we mean by limits involving infinity. Sometimes you may want to see how your function behaves as you move away from the origin, too far away from the origin. And that we will show with x goes to infinity or x goes to minus infinity. So in both cases, you are too much away from the origin. And the question here, how does your function behave? More specifically, whether your function gets close, arbitrarily close to a constant or not. Because sometimes when you go to infinity, your function values may go to infinity too. So what we are looking here is what happens if I move away the origin too much. Does my function get close to a constant number? Now this is an example. Y is equal to 1 over x. As you see, as x goes to infinity or minus infinity, the absolute value of x becomes very, very big. So this function goes to 0 as x goes to plus infinity or minus infinity. So that's the basic idea, and that's how we define, rigorously define what we mean by going infinity and going minus infinity. We say that f of x has the limit L, which is a constant number, as x approaches infinity, and write this expression. Limit as x goes to infinity of f of x is L. The condition is now, for every epsilon you give me, there I must find a number n, probably a big number n, so that f of x minus L is less than epsilon for all x greater than n. Okay, so what I'm trying to show here as I go to plus infinity, the difference between f of x and L becomes more and more small. And at the end, we will become 0 if I can show this. Similarly, we say that f of x has the limit L as x approaches to negative infinity, and write limit as x goes to negative infinity of f of x is equal to L. For every epsilon greater than 0, I must find a number such that f of x minus L is less than epsilon if x is smaller than n. And here should be a big negative, a negative number with that be the big absolute value. So that tells me that as I approach minus infinity, f of x minus L will become 0. The limit will become 0. So that's limits. That's limits at infinity. We are looking limits at infinity. We have given an example in the previous slide. Let's go over this example. Okay, that's 1 over x again. Suppose you give me an epsilon. It could be a small number. And we want to show that as x goes to infinity, the function goes to 0, and as x goes to minus infinity, the function goes to 0. What shall I choose for the positive side? Well, I can choose m is equal to 1 over epsilon. And on the negative side, I can choose n is minus 1 over epsilon, which will be a negative number. So if you give me small epsilon, I will choose delta as 1 over epsilon or minus 1 over epsilon. And after some number n, as shown here, I will be close to 0. And as you can see, if I move further, this will get closer and it will get arbitrarily close to 0. Now on this side, if I choose n as minus 1 over epsilon, that shows this minus epsilon. That's given. So after if I move further left here, it will become more and more close to 0. It's a negative number, but it goes to 0. Okay, so that's the basic idea. The way to prove that your function has a limit at infinity or minus infinity, you have to find a number. So plus infinity, this number must be so that m, for all x greater than m, your function should stay in this interval on x-axis between 0 and epsilon. For this side, or for negative infinity, that's minus infinity. And after this, the function must stay in this 0 minus epsilon band. And so if I can do that for some function, then I can show that my function has a limit at infinity. Let's continue. All the limit laws in theorem are true when we replace limit x goes to c by limit x goes to infinity, or limit as x goes to minus infinity. Okay, so the limit laws doesn't change when you go to infinity or when you move away from the origin to see how your function behaves. Let's look at this function now. 5x squared plus 8x minus 3 divided by 3x squared plus 2. Okay, so I have proved that 1 over x goes to 0. So 1 over x squared also goes to 0. 1 over x cubed also goes to 0. So when I want to find the limit of this function as x goes to infinity, divide both the numerator and denominator by x. So you have 5 here, 8 over x, and minus 3 over x squared. And in the denominator, you have 3 plus 2 over x squared. Now these terms go to 0. 1 over x minus 1 over x cubed, 1 over 2 over x squared all go to 0, and your limit is 5 over 3. So your function approaches to 5 over 3 as you move to infinity. Now on this side also the same is true. You again do the same thing, and here you approach this line from above, here you approach this line from below. If we continue, let's look at this function. 11x plus 2 divided by 2x cubed minus 1. Okay, now I can divide both the numerator and denominator x to the power 3. So I'll have here in the numerator 11 over x squared and 2 over x cubed. And here I will have 2 minus 1 over x cubed. So these are 0, that's 2 minus 0, so the limit is 0. Again, this function on both sides approaches to 0 when x goes to infinity, and when x goes to minus infinity, the same approach, the same apply. Now we give a special name to these lines. The line y is equal to b is a horizontal asymptote of the graph of function y f of x if either f of x limit as x goes to infinity of f of x is b, or limit as x goes to minus infinity is b. So we call these horizontal asymptotes, and therefore that's important in drawing the graphs. It's important to know the asymptotes. Now that was limit at x infinity. Now let's look at this function. X cubed minus 2 again, x cubed plus absolute value of x cubed plus 1. Now, when you go to plus infinity, this is plus and this is plus, of course, absolute value. If you divide x cubed by absolute value of x cubed, 2 over absolute value of x cubed will go to 0. 1 over absolute value of x cubed will go to 0, and we will have 1. So y equal to 1 is a horizontal asymptote for this function. Now what happens if I go to minus infinity? Again, I did each numerator and denominator by x absolute value x cube. Now here x cube is negative, but absolute value of x cubed is a positive number. If I divide by absolute value of x cubed, this one and this one, these will go to 0 as it goes to minus infinity. And we are here have minus 1. So there are two horizontal asymptotes for this function. One is y equal to 1 as x goes to infinity. Y is equal to minus 1 as x goes to minus infinity. So this function has two horizontal asymptotes. Let's look at this function. Y is equal to x times sine 1 over x. It wild oscillates here, but we don't care about this because we want to know what happens as x goes to infinity or as x goes to minus infinity. As you see from the graph, this function approaches the line y is equal to 1 as x goes to plus infinity, and y is equal to minus 1 as x goes to infinity. So horizontal asymptote for this function is y is equal to 1. Let's look at this function. Y is equal to 2 plus sine x over x. Now, as x goes to infinity, sine x over x goes to 0 because the absolute value of sine x is maximum 1. However, x goes to infinity, so this is less than or equal to 1 over x. This term goes to 0, and y goes to 2. So y is equal to 2 is a horizontal asymptote for this function. And the function crosses the horizontal asymptote infinite number of times, but each time it gets closer and closer. Now that's another one. Here we have x squared minus 3 divided by 2x minus 4. Now, as you can see, the numerator polynomial degree is 1 greater than the denominator. In this case, I can make a polynomial division. I divide x squared minus 3 by 2x minus 4. What I get is x over 2 plus 1, plus 1 over 2x minus 4. So these are the same expressions. Now, as x goes to infinity, as you can see here, this function goes to infinity. It does not go to a constant number. But what happens here is this. when you go to plus infinity, your function value is this value plus some positive value. So your function, this is a line actually, and it's given here, this red line. So the function value is greater than the value on this line, but it gets arbitrarily close to this line. We call such asymptotes, this is an asymptote also, but it's oblique asymptote. It's not horizontal, it's not vertical, but it's an oblique asymptote with a slope greater than 0. Okay, so when you go to minus infinity, what happens? This number is here, and that's now a negative number. So you're subtracting this number from this number, basically. So your function value is less than the value of this line. So when you go to minus infinity, you also approach the same oblique asymptote. You get arbitrarily close to it, but from below. So it depends on the value of this function, whether it's positive or negative. If positive, you're adding. So your function is greater, your function value is greater than the value of the value on the asymptote. If it's negative, you're subtracting, and your function value is less than the value on this asymptote. So we have defined now a horizontal asymptote and an oblique asymptote. Oblique asymptote appears in rational function if and only if the degree of the numerator is 1 greater than the degree of the denominator. So when you divide, you get a line. Okay, so we talked about limit at infinity. And in certain cases, this is an asymptote, horizontal asymptote. And in certain cases, as we gave in the previous slide, the function may go to infinity, but may approach to an oblique asymptote. Now we are going to look at the case where x approaches a constant number c. The limit of the function might be infinity. Actually, this does not mean there is a limit. But if the function grows too much as you go to c, then we show this as infinity. It does not mean that the limit exists, but we call it infinite limit. And the case when we can do this is this. If every positive real number, there exists a corresponding number delta, such that for all x in this interval except c, f of x should be greater than. That means you can give me any big number you want, but I'll always find a delta such that for all x in this interval, my function will be greater than the number you give me. This is actually a two-sided case because that's a symmetric interval. Similarly, we say that f of x approaches negative infinity as x approaches c, and write this limit as x approaches c of f of x is minus infinity. If for every negative real number, so b is a big positive number and minus b is a negative number with big absolute value. So if you give me this number, I can find a delta greater than 0 such that for all x in this interval, my function will be less than minus b, which means the absolute value of my function will be greater than the absolute value of b. But since it's a negative number, we say it's less than b. So if b is minus 10,000, my function will have values less than minus 10,000. It might have 12,000, 13, minus 12,000 or minus 13,000. So that tells me that if I can find this interval, it tells me that as x approaches c of f of x is minus infinity. So that's not the existence of a limit, but for certain functions, the behavior of certain functions around some number c may be either growing too much or getting smaller too much, like an x infinity case. So that's why we write this. As I said, the definition above is for two-sided limits. There are one-sided infinite limits too, okay? Now, you may approach x of 0 either from the right-hand side or from the left-hand side, and the limit may be infinity again. So here, in order to show that one-sided limit exists as x approaches to some x of 0, if every possible large number b, there exists a corresponding number delta such that all x in this interval, x of 0 plus x of 0 plus t. So x is greater than x of 0, less than x of 0 plus d. So for all x in this interval except x of 0, f of x should be greater than b for going plus c. For minus infinity, again, you will have an interval x of 0 minus d, x is greater than x of 0 minus delta, which is less than x of 0. So for all x in this interval, there is a misprint here. F of x should be less than minus b. Or f of x, f of x is greater than b. True, that's for the, if we are going to, that's for positive infinity. Now for negative infinity, we write this. X approaches to x of 0 either from the right-hand side or from the left-hand side. We say that it's minus infinity. If for every possible large number b, for all x in this interval, that's less than minus b. And for all this in this interval, f of x is less than minus b. So that's for minus infinity case. Okay, so let's go back to the 1 over x function 1 over x. Now, if x goes to 0 from the right-hand side, this number is positive and the limit is infinity. The function grows too much. Where x goes to 0 from the left-hand side, 1 over x is a negative number and it goes to minus infinity. For this, it's enough to choose delta is equal to 1 over b. Okay, let's look at this. Okay, so here is a pictorial representation. As x goes to 0 from the right-hand side, the function goes to plus infinity because 1 over x is a positive number and it grows very fast. However, I can find an interval on the right of 0 so that for all x in this interval, this is greater than the number we give me. So what I choose is 1 over b. For minus infinity, you choose minus b, and you can find an interval around left interval around 0, so that my function value is greater than in this interval, greater than the number you give me. Let us show this algebraically. Okay. So here is another function. y is equal to 1 over x minus 1. Now, as x approach 1 from the right-hand side, you can see that this number becomes very, very small, but it's positive, so it goes to positive infinity. If x approaches 1 from the left-hand side, then x minus 1 is a negative number because it's approaching from the left-hand side, and I can choose again 1 over b as delta and find an interval around 0 so that my function is less than minus b. So let's do it algebraically. Delta I choose is 1 over b, so this is a right interval on the right of b. X is greater than 1 and less than 1 plus delta, that's 1 over b. So I look at 1 over x minus 1. Now x is less than 1 plus 1 over b. I substitute that, so since x is less than this part must be greater, because I am dividing by a greater number here, which is 1 plus 1 over b. So x minus 1, 1 over x minus 1 becomes 1 plus 1 over b minus epsilon. Ones cancel out, that's b. So my function value is greater. Now, if I look at on the left side, I choose 1 minus 1 over b is less than x, which is less than 1. That's an interval to the left of x equal to 1. Okay. Now, here I substitute 1 minus 1 over b here. So this is a number which is less than x. So this is less than this number because x is less than 1 minus 1 over b. So 1 cancel out, and that comes minus b. So my function goes to minus infinity, and you give me any big number, any negative number with big absolute value. I substitute this interval, and x is less than 1 minus 1 over b. So this inequality holds, and my function value is less than minus b. That means the absolute value of my function is greater than the absolute value of b. If b is minus 10,000, my function is maybe minus 11,000. So it will be less than 10,000, minus 10,000. Okay, this is our one-sided limits. Okay, now that's a two-sided case. Limit as x approaches to 0 from the right-hand side is positive, 1 over x squared. Left-hand side it's positive, so it is two-sided. So we write just limit as x goes to 0, 1 over x squared is infinity. In this case, what's the delta we should choose? Delta we are going to choose 1 over square root of b. Okay? So around 0, I will have this length 1 over square root of b, and this length 1 over square root of b, and so 1 over x squared will be greater than b always. Okay, so that's the two-sided case. So what we are basically doing here, for a given geometrically, for a given number, we suppose that speed, it's a big number, it could be 10,000, 12,000. You build now, since this is a two-sided case, a symmetric interval around C. Now, the interval on the left is bigger than interval on the right. But if I choose the interval on the left, I will go here, which will be out of this range. I will not be greater than b, but less than b. So we again choose the minimum here and prove that my function, the limit of my function is infinity. That's similar to the normal limit case. Okay, that's for going to minus infinity. So you give me a negative number. This could be minus 100,000. Now, this line, horizontal line, cuts my graph at 2 points. Here on the left-hand side, you have a bigger interval. This is a smaller interval. But since I'm going to build a symmetric interval around C, I should choose again this one as delta. This one for delta. So then I will be sure that my function value is less than minus b. If I choose a big one, so I will come something here, I won't be less than minus b, but I will be greater. So always choose delta as the minimum one, minimum length interval on the right and on the left. Okay, now we give a special name for these limits, and we call them vertical asymptote. So it's different from horizontal asymptote and vertical asymptote. Let's get a line x is equal to a is a vertical asymptote of the graph of a function if either limit as a goes to x goes to a from the right hand side, it's plus or minus infinity, or as x goes to a from minus side, plus or minus infinity. So these we call vertical asymptote, and they are important for graphing your function. Let's look at now certain limits. Here we have x minus 2 squared divided by x squared minus 4. Now, I'm going to look at a limit as x approaches to 2. That's 0 over 0, because when I put x is equal to 2, result is 4, so this is 0 and this is 0. That's not a real number. But I can cancel out these x minus 2's. I have x minus 2 here and x plus 2 here. Now, as x approaches to 2, it's 0. That's not a infinite limit. However, if x approaches to minus 2, then that will be a different story. You will have a vertical asymptote. Let's look at this one. So x minus 2 cancel out. If I factorize this, I have 1 over x plus 2, and the limit is 1 over 4. Of course, there's no problem here. If I go to x goes to 2 from the right-hand side here, with this, now I can factorize this as x minus 2, x plus 2, and this is x minus 3. So as x goes to 2 from the right-hand side, this is positive, but this is negative. So the limit is minus infinity. Now we can say that x is equal to 2 is a vertical asymptote. Let's look at this one. X minus 3 and divided by x squared minus 4. What happens if I approach 2 from the left side? Now, I again factorize. Now, this is negative, this is positive, this is negative. So the result is positive. So limit as x goes to 2 from the left-hand side, you have positive infinity. Okay, final one, 2 minus x divided by x minus 2 cubed. Now I can cancel out 2 minus x is minus x minus 2. So I can cancel out all of them here. That's minus 1 over x minus 2 squared. Now that's a positive number since it's a square, but that's negative, minus 1. So the function goes to minus infinity. In this case, x equal to 2 is a two-sided limit. Okay? So these were a couple of examples on the limit. Let's look at this, x plus 3 over x plus 2. Now it's obvious that when x goes to 2 from the right-hand side or left-hand side, the function minus 2 from right and left, the function goes to minus infinity on the right and plus infinity on the right. So if I approach x from the plus side, this is plus, so you go to plus infinity. If I approach minus 2 from the left-hand side, okay, now this is minus, this is 0, sorry. Left-hand side, it's okay, left-hand side, minus 2, sorry. So that's negative number, but that's a positive number. 3 is greater than minus 1, so you go to minus infinity. So we have a vertical asymptote at x equal to minus 2. Now let's look at the horizontal asymptote. When x goes to plus infinity, what happens? Okay, this I can write by polynomial division like this. 1 plus 1 over x plus 2. Now if I go to infinity, this becomes very, very small and my limit is 1. So there's a horizontal asymptote. Y is equal to 1, as you can see, is a horizontal asymptote. But here, if I go to plus infinity, this is a positive number added to 1. So my function value is greater than 1. Although it's very small, still greater than 1 when x goes to infinity. However, on the negative side, if I approach minus 2 from the if I approach minus infinity, that's a negative number subtracted from 1, of course. So my function value is less than y. So that's why I approach from above to my horizontal asymptote. Here I approach my horizontal asymptote from below. And this actually shows, so whether x goes to plus or minus infinity doesn't make any difference. This is equal to 1 because this goes to 0. When you approach minus 2 from the right-hand side, that's plus infinity. If you approach from the left-hand side, minus infinity. So we have vertical asymptote at x equal to minus 2 and one horizontal asymptote, which is y is equal to 1. Okay, there's another example, minus 8 over x squared minus 1. Okay. Now, as you can see, when x is plus or minus 2, we have 8 divided by 0, which is not a real number. So let's see, if I approach 2 from the left-hand side, what happens? That's minus, because I'm approaching 2 from values less than 2. That's a negative number, but there's a negative sign here, so that's a positive number. So I go to infinity. Now, if I approach 2 from the right-hand side, that's a positive number, but there is a negative one. I approach to minus infinity. Now, let's look at minus 2. If I approach minus 2 from the right-hand side, from values greater than 2, what happens? If I approach from minus 2, that's positive, that's still greater than, that's x squared is, if you approach from the right-hand side, x squared is less than minus 4 because the absolute value of x here is less than 2. So again, this is minus, I go plus infinity. If I approach minus 2 from the left-hand side, then this is positive because I can approach from values, absolute value greater than absolute value of minus 2. So that's positive, that's negative, so I go to negative infinity. Now, these are vertical asymptotes. How about the horizontal asymptote? When x goes to plus infinity, you have what? That's a negative number, and that goes 0 from values less than 0. Sorry, yeah, that's a negative number from values less than 0. If I go to minus infinity, it doesn't make any difference because I have x here. Again, I approach 0 from below. Okay, so y is equal to 0 is a horizontal asymptote. And I approach this asymptote from below because that's a small number as x goes to infinity, but it's a negative number. As x goes to minus infinity, that's a small number, but negative small number. So I'm below these lines. Okay, this is shown here. Limit as x goes to 2 from the right-hand side is minus infinity, like here. Limit as s goes to, okay, that's the same thing. Oh, minus, so limit as x goes to minus 2 from the right-hand side, again plus infinity, as we have shown here. So that's minus infinity, that's plus infinity. As you can see, left-hand side approach to 2 and right-hand side approach to 2. And this is right-hand side approach to minus 2, and this is left-hand side approach to minus 2. And the limits are given here. So x is equal to plus or minus 2. There are two vertical asymptotes. That's plus 2 and minus 2 for this function. Let's continue. Now, these are the graphs of some trigonometric functions. They have y is equal to tangent x has infinite number of vertical asymptotes. At pi over 2, 3 pi over 2, 5 pi over 2, or minus 1 over 2, minus 3 over 2, minus 5 over 2, etc. Because tangent x repeats itself with period pi. So between minus 2, minus pi over 2, plus pi over 2, another thing like this, etc. Now, secant x is positive if x is between minus pi over 2, plus pi over 2, and as x goes to plus pi over 2 and minus pi over 2, secant x goes to infinity because it's 1 over cosine of x, and cosine of pi over 2 and minus pi over 2 are 0. But if you approach pi over 2 from the right-hand side, what happens? You go to minus infinity because cosine is negative for angles greater than pi over 2. And 3 pi over 2 also, that's the same thing. So these have a lot of infinite number of vertical asymptotes. Okay, so this is the same thing that we have shown before, almost the same thing. So let's look at these limits too. Let me just make it a little bit bigger. Okay. Okay, x cubed, x squared minus 3 divided by 2x minus 4. Now, as you can see, the degree of the numerator polynomial is 1 greater than the degree of the denominator polynomial. So I can make a division, polynomial division. I divide x squared minus 3 by 2x minus 4. I get 1 over 2x plus 1, and that's the remainder, 1 over 2x minus 4. Now, what happens as x goes to plus or minus infinity? Actually, as x goes to plus or minus infinity, this is the dominant part. This becomes very, very small. So my function value approaches this line, which is an oblique asymptote. The limit is infinity, of course. There is no limit, but there is an oblique asymptote, and my function value as goes to plus infinity, since it's a plus number, this part, is greater than the value of this oblique asymptote at the same point. And as x goes to minus infinity, this is a negative number, and so my function value is less than the value of on this line, on the oblique asymptote. And we can also look at so that's infinity, it's infinity. If it goes to minus infinity is minus infinity, but here I am below the oblique asymptote. Here I am above the oblique asymptote. Now, 2 is a critical number. Here, when x is equal to 2, the denominator is 0, but the numerator is not 0. So there's a vertical asymptote here at 2, because as x approaches to 2 from the right-hand side, this is positive, and this is positive too. So the limit is infinity, plus infinity. Now, if I approach 2 from the left-hand side, and this is negative, but again, this is positive because that's x squared, so that's greater than 3. So you go to minus infinity. So x is equal to 2 is a vertical asymptote, and the line 1 over 2x plus 1 is a two-sided oblique asymptote. Okay, my function gets arbitrarily close to this line, which is the oblique asymptote. Let's continue with the last figure. Now, we talked about asymptotes, which gives an idea about how my function behaves if I go to infinity. If I move too much away from the origin. So these are limits at infinity. Sometimes your function becomes very big or very small when you approach a constant number. So these are the infinite limits. Limits at infinity and infinite limits. And asymptotes are useful to visualize how your function behaves. Now, this is not. This does not show an asymptote that's 3x to the 4 and some other function with 3x to the 4 and other x's with lower degrees. Between minus 2 and plus 2, you look at these two functions, blue and red, they are different. But if you squeeze this, I mean, you get minus 20 plus 20, there's almost no difference between these functions. So that's that's not an asymptote, but it's a useful practice comparing two functions when you move away from the origin. If you squeeze this, instead of minus 2, you look at this window, and this function, blue function, behaves like this function if you look from away. Okay, so that's the end of chapter 2 recordings. I would suggest you listen to these recordings because there is no noise problem or sound problem. And so I will start after this chapter 3. Okay, see you on Monday.